A warm welcome to the 9th lecture on the subject of digital signal processing and its applications. We will spend a minute or two in recalling what we did in the previous lecture and then invite questions if there are any before we proceed. In the previous lecture, we had put down the properties of systems, and we had also just begun our discussion of going into an alternate domain. We said that if we look at the expression which relates the input to the output with an input equal to a complex exponential in an LSI system, the relation involves a constant which depends only on frequency. That constant, we saw, could be viewed as an operation between the impulse response and the sequence e raised to the power j omega n. And we had concluded the previous lecture by noting that we could perhaps give it an interpretation which relates to projection of the impulse response, or taking a dot product of the impulse response in some way. Alright? So, we now need to make these ideas more concrete. That is the objective of the lecture today, and also to take us to the first transform domain that we are going to discuss. We shall also in this lecture identify what we mean by a transform domain in general, and in particular we shall be talking about the discrete time Fourier transform. So with that then we begin the lecture today, but before we continue our discussion, since this is going to be a very important new aspect of discrete time signal processing, we could spend a couple of minutes in asking whether there are any questions which immediately need to be answered. Yes, there is a question.
Strategy of selecting the troublesome input is a bit unclear.
Okay, yes.
Actually, we are choosing some troublesome input which give rise to some transients like step input and all, which is also a bounded one. Why like that?
Okay, so the question is, in the previous lecture we had looked at the proof of the condition for stability being necessary. That is, we had seen that if an LSI system needed to be stable, then its impulse response needed to be absolutely summable. We had proved sufficiency with great ease, but to prove necessity we needed to use what we called a troublesome input. So the question is that choice of troublesome input, and the reason why we proceeded with that input was not very clear. So let's quickly identify the main steps or the main reasoning that went into that so-called troublesome input. You see? So this is essentially a review and clarification of points from previous lectures. So the first point is necessary condition for stability. Now you see, what we did was to take an LSI system with impulse response Hn. We gave an arbitrary input xn and noted that the output yn in general is summation k going from minus to plus infinity xk hn minus k, or hk xn minus k, whatever you please. Now in particular we said consider n equal to 0. We said for that n, y of 0 is summation k going from minus to plus infinity xkh minus k. Now our reasoning was that we can choose a troublesome bounded input input xn, and we chose that troublesome bounded input as xk or xn is h conjugate minus n divided by mod h conjugate minus n. Well, I mean, conjugate or it does not matter here. Whenever h minus n is not 0 and 0 otherwise. Now, one point which perhaps may not have been so clear in the previous lecture is that this input is actually bounded. Maybe that point was not emphasized enough. In fact, if you happen to look at this xn, the modulus of xn for any n here, because any sequence is really like a vector in an infinite dimensional space, and the infinity of that dimension is the infinity of the integers. You can think of each sample of the sequence as a coordinate of that so-called vector. So, a sequence is like a vector in a countably infinite, this is, when we say in a countably infinite dimensional space, whose orthonormal basis is essentially the set of all unit impulse sequences. Put a unit impulse at every integer location, and each of these gives you a separate perpendicular vector. This is a generalization from what we have in this 5-dimensional space here. You see, you can think that if you were to generalize this here to in 5-dimensional space, of course you are putting the ones respectively at the locations 0, 1, 2, 3 and 4. But you can keep generalizing this. You can put this at each integer location, and each of them gives you a new perpendicular vector. And that's how you have an orthonormal basis for the space of sequences. And of course, we know very easily how we can express any sequence in terms of this perpendicular basis. That we've already done when we were trying to derive the principle of convolution. So we saw that any sequence, any vector or sequence xn can be expressed in terms of these. That's very easy. Xn is summation k going from minus to plus infinity, xk delta n minus k. In signal processing, it's very interesting, like in poetry. The same lines can have many meanings. The same equation can assume many meanings in signal processing and communication, and one must learn to appreciate that. So this very equation here had a different meaning when we talked about convolution. There we said that you're thinking of it, of course in a way it had a, there's a relationship between that meaning and this, but still there we were trying to express all sequences in terms of the unit impulse. Now here what you're trying to do is to show that you have an orthonormal basis, and in fact we'll show in a moment that it's orthonormal, and that the orthonormal basis can allow you to expand any vector in terms of it. So it's the same, one equation can have several meanings or several different interpretations or several nuances of interpretation, and one must learn to appreciate that as we go along. Anyway, so coming back to this, it's very clear that we can express xn in terms of this orthonormal basis, but what we now need to see is why are we calling it orthonormal. So we need to talk about a dot product. You see, the dot product between two sequences is, as we generalize from finite dimensional spaces, the dot product would be essentially a sum over all the coordinates. You see, each k is a coordinate now. Each location is a coordinate. x1n, x1k, x2k, and for the moment let's assume real sequences. x1, x2. At the moment we are assuming real sequences, and we are assuming the coordinates are real. So this is essentially a generalization from what we did in finite dimensional spaces. We took the product of corresponding coordinates and we added up over all the coordinates. But now we need to ask whether this definition is acceptable when the sequences are complex. So for that we need to ask what more do we want from a dot product. Before we do that, since we are generalizing the idea of a dot product, we would like to use a slightly more general notation for dot product. So the dot product is also more generally called the inner product. And it's denoted by the inner product of x1, x2 like this, with triangular brackets. Now, you see, if you take the dot product of x with x, what do you get? In conventional vector algebra, we get the magnitude square of the vector. And here, we would like to use the notation norm. So instead of saying magnitude for a vector in general, for this generalized class of vectors, we call it the norm. In fact, we call it the 2 norm. So don't worry too much about this lower 2, but the upper 2 is essentially a squared. This is what is called the L2 norm. This is a technicality, let's not worry too much about it, but let's write it down for completeness. I mean, you could have other numbers here also. However, in our discussion in this course, we shall not keep writing this subscript 2 after this. We shall understand that it is the 2 norm. Now, you see, one thing, this norm is the generalization of the idea of magnitude. So instead of using the word magnitude for this generalized class of vectors, we call it the norm. It's the same idea. But you see, what do we want of a norm? We definitely want that a norm or a norm squared be non-negative. In fact, we want the norm to be not only non-negative, if the vector is 0 only then we would allow it to be 0. If there is a non-zero vector, we definitely do not expect that it should have a 0 magnitude. Okay, so we want the dot product of x with x to be greater than or equal to 0, and we want dot product of x with x to be equal to 0 if and only if the vector x is itself 0, which means xn is equal to 0 for all n. Is that correct? But you see, if we take the definition of the dot product or the inner product that we just used a few minutes ago, if we take the dot product or the inner product of x1, x2 to be summation k over all the integers x1k, x2k for complex x1, x2 as well. If we do this, then what are we going to land up with? We are going to land up in the troublesome situation that the inner product of x with x is simply summation k going from minus to plus infinity x squared n, but x squared n when xn is complex could be complex, and summation over k x squared, of course this should be k, sorry. So summation over k x squared need not be 0, need not be non-negative. In fact, it can be complex in general, and we definitely do not want that. We want it to be a magnitude squared, so that can only be non-negative, and it should be 0 only if x itself is 0. Is that correct? Now, you see, how do we then correct the situation? It's very clear that we want each of these terms in the summation to contribute a non-negative quantity. And that can be done only if you have a modulus in each of the terms. And that modulus can appear only if you bring in a complex conjugate. And therefore, we redefine the dot product in general for complex x1, x2. We need to redefine the dot product of x1 with x2 to be summation k going from minus to plus infinity x1 k x2 k complex conjugate. No doubt this makes no difference for real x1 x2 at all. The definition for real x1 x2 is as it is. Is that clear? Yes. You see, now it's very clear. Now, of course, once we have done this, we have taken care of the problem. So now we have the inner product of x with x is equal to summation k going from minus to plus infinity mod xk squared. It is xk complex conjugate, which is summation on k mod xk squared. This is of course greater than or equal to 0. It is 0 only if, in fact if and only if, xk is equal to 0 for all k. Unless each of those terms is 0, this cannot sum to 0, because each term there is non-negative. And therefore, we have achieved what we want out of the dot product. We have been able to redefine the dot product in such a way that it takes care of this use of the dot product for calculating the magnitude squared of a vector. Now let us interpret the so-called frequency response that we wrote the last time in the language of the dot product. So we have h omega that we wrote the last time is summation k going from minus to plus infinity hk e raised to the power minus j omega k, and it's obvious that this is the dot product of the sequence h with the sequence e raised to the power j omega n. Now this dot denotes the independent variable in the sequence. So when we write a dot like this, what we mean is that we are treating the whole sequence as an object. We are not taking an individual sample. So the dot means, otherwise if we write n, we could write n if we are careful, but when we write n, the tendency is to think of the nth sample only. And here we are not talking about a specific sample. We are talking about the whole sequence as an object. That's very important. And that's why we put a dot there. More than the question of notation, it's the philosophy behind this that matters. That's why we have to be careful with notation. It's not so important that we should be very fussy about notation all the while. But the thought behind the reasoning should not be lost. So when we take a dot product, it is not enough to look only at a part of the sequence. A dot product involves the whole sequence. That is what is being emphasized here. Anyway, now you see, there's a very interesting interpretation that we have just given, this whole concept of, the whole concept of frequency response. What we have said is that if you have this LSI system S with an input e raised to the power j omega n, so you have given a complex exponential as the input, you get h omega e raised to the power j omega n coming out, and h omega is essentially the inner product, the dot product or the inner product of hn and e raised to the power j omega n. Now we already know what an inner product does in conventional small dimensional physics or engineering. When you take the dot product, I told you, of one force in a certain unit vector in a direction chosen, so if you have chosen a certain direction, and if you take the dot product of a force vector with a unit vector in that direction, what you have done is to resolve the force in that particular direction, to find the component of the force that acts in that direction. Now what we are saying here is that h omega is like the component of the impulse response that acts in the direction of e raised to the power j omega n. In fact, it's an exact interpretation. It's not just very vague or, approximate. It's exactly what we are saying. We are saying that if you give e raised to the power j omega n to an LSI system, and if h omega converges, that means if the sum hk e raised to the power j omega e raised to the power minus j omega k over all k converges, then this quantity h omega is like the dot product of the impulse response in the direction of that complex exponential. The dot product is a number, it's a complex number. And the physical interpretation of that complex number is that the magnitude of that complex number multiplies the amplitude of the complex exponential. And the angle of the complex number adds to the phase of that exponential. So in fact here, another way of understanding this is through the notion of eigenvalues and eigenvectors. You see, what are we saying in effect? We are saying here that when you put the sequence into the system, what comes out is the same sequence multiplied by a constant. Now this is not going to happen for all kinds of sequences. If you had, a sequence which is square-like in nature, square wave-like in nature, it's not going to happen for an LSI system in general. But for a complex exponential, this happens. When you put in a rotating phasor into the LSI system with impulse response Hn, out comes the same rotating phasor but multiplied by a constant. Now such a sequence which goes into a system and emerges as the same sequence but multiplied by a constant is called an eigensequence of the system. Sequence that goes in, that is unchanged in form, as it emerges. It's like saying that the action of the LSI system is decoupled for each of these sequences. You understand this better if we can do one more thing. Suppose, by whatever means now, you could express any sequence. You see, remember, you did this earlier. You expressed any sequence xn in terms of these impulse sequences delta n minus k. So you wrote any sequence xn as summation k xk delta n minus k. So you were able to express any sequence in terms of the unit impulses. Now suppose by whatever mechanism you are able to express any sequence as a linear combination of such rotating phasors, rotating with different angular velocities. Then what we are saying here is, if I take any one of those phasors that comprise the input, the response of the system to that component of the input is only the same phasor multiplied by a constant. So if I decompose the input along each of these phasors, so to speak, for different omegas, then what I am saying is the response to the phasor at a particular angular frequency omega has nothing to do with the the phasor at some other omega. They are all decoupled, they can be treated separately. Slightly deeper issue, but we will understand this better as we go along. So in other words, what we are saying is, I mean, let me try and bring this a little more, it takes a little time to absorb this. What we are saying is, take the same system S, LSI HM. Suppose instead of giving e raised to the power j omega n, you give A1 e raised to the power j omega 1 n plus A2 e raised to the power j omega 2 n plus A3 e raised to the power j omega 3 n. Out would come A1 h omega 1 e raised to the power j omega 1 n plus A2 h omega 2 e raised to the power j omega 2 n plus A3 h omega 3 e raised to the power j omega 3 n. This is not at all difficult to show from the property of linearity or additivity, and the property that when you put in e raised to the power j omega n, out comes e raised to the power j omega n multiplied by h omega. So what we are saying is the action of the LSI system on each of these components is decoupled. I don't have to worry about what A2 and A3 are when I am calculating the output to A1 e raised to the power j omega 1n. When I am calculating the output to A2 e raised to the power j omega 2n, I don't need to worry what A1 and A3 are. There is a decoupling. Now carry this argument to its limit. So if you could, here I am taking a very specific input which had only 3 such e raised to the power j omegas, only 3 such frequencies. Suppose I use a continuum, I use all the frequencies omega from 0 to 2 pi or all the frequencies from minus pi to pi. Incidentally, now we make a remark about what range of values omega can reasonably take. Omega is the normalized angular frequency. Now, on the frequency axis, there is aliasing or there is repetition. Beyond omega between minus pi and plus pi. You see, the reasoning for that is very simple. What does omega equal to 2 pi correspond to? Omega equal to 2 pi corresponds to sampling frequency. And we have agreed that every sine wave is comprised of 2 oppositely rotating phases. If a sine wave has frequency omega, it comprises of 2 phases, one rotating clockwise with frequency omega and one rotating anti-clockwise with frequency omega. In other words, if you take both to be in the clockwise or anti-clockwise direction, one with frequency omega and one with frequency minus omega. 2 phasors come together to form a sine wave. So on the phasor angular frequency axis, each pair of frequencies omega and minus omega come together to form a sine wave. and obviously their magnitudes, the two phases have to have the same magnitude and opposite starting angle or opposite phase. Now, we've seen that when you sample, you take the original set of frequencies or original frequency axis, whatever it is, shift it by every multiple of the sampling frequency, and these shifts are added. On this normalized scale, the sampling frequency is 2 pi. So you are going to take the original spectrum, shift by every multiple of 2 pi and add up these shifted versions. Let's show that graphically. Whatever there is, you are going to shift this by every multiple of 2 pi and you are going to add them. Now obviously if you don't want these shifts to overlap, this must remain between minus pi and pi, and of course that's also obvious from what we have seen in the sampling theorem. The maximum component that you have in the original signal should not be more than half the sampling frequency. So that means the so-called unique omegas that we can deal with are only between minus pi and pi. So when we take any input xn and ask whether it can be expressed as a linear combination of e raised to the power j omega n, we need only to worry about the omegas going from minus pi to pi. Of course, the frequency axis is continuous. So, I am not going to be able to use a summation now. I need to integrate the limit of a summation as the variable of summation becomes continuous is an integral. Right? So, what we are saying is, suppose, I am trying to motivate the whole idea. Suppose I take the same LSI system once again, give to it a combination of x omega e raised to the power j omega n. You know what I mean by x omega? X omega is the component of xn along e raised to the power j omega n. So what I am saying is, suppose you are able to decompose, just like you decompose the impulse response, suppose you are also able to decompose the input along different e raised to the power j omega n's. And you did this for all the omegas going from minus pi to plus pi. Then it means that, since minus pi to plus pi is exhaustive, putting those components back should give you back xn. So what we are saying is, what we are trying to ask is what comes out here, isn't it? And we are saying, in particular, here when you take x omega e raised to the power j omega n, what will come out? So x omega e raised to the power j omega n is going to give us x omega h omega e raised to the power j omega n. Is that right? And therefore, if you integrate this, if you integrate over omega here, you can also integrate over omega here. And how can we say that? That's because of the property of linearity. If for each omega I can do this, I can do it for the combination of the omegas. Now this will lead us to a very interesting property of this inner product. This inner product of a sequence with a rotating phasor gives us a new domain called the discrete time Fourier domain or discrete time Fourier transform domain. We shall see more of this in the lecture to come and build up in greater depth the whole idea of the discrete time Fourier transform in the coming lecture. Thank you.